To continue with our discussion on the coherent states, let us see some more properties on the coherent states. And let us start with the scalar product of two coherent states. So, let us see what we understand or what we learn from this scalar product. Of course, you know that the Fock states, which are the occupation number states denoted by n, which are the eigen states or eigen functions of this operator n, capital N, which has a form which is A dagger A. This is a Hermitian operator, which means that it gives real eigenvalues. And also that this are orthonormal states. So, one Fock basis is orthonormal to another Fock basis, and however, the state alpha, which is a coherent state, it has complex eigenvalues, and it's an eigenfunction of the operator A, which is a lowering operator, which is not a Hermitian operator. So, it's a eigenstate of non-Hermitian operator. Let us write it here. So, please take a note that we have explained this, or rather we have stated all of these facts earlier, and this non-Hermitian operator is A, that is the lowering operator, and it has complex eigenvalues. Thus, it is not clear, it is not automatically clear that the coherent states are orthogonal. Which is and of course, they are distinct than the Fock states, as we have seen earlier, and so it needs to be ascertained that whether these are orthogonal states, and in order to do that, let us take two coherent states alpha and beta, and look at the inner product between them. I am just writing it as beta alpha, which we know that by definition it is d dagger beta d alpha 0. So, this can be written as so these zeros are the vacuum states, and this d dagger and d dagger beta and d alpha are basically the translation operator that we have learnt earlier. So, this is exponential minus beta A dagger, exponential beta star A, exponential alpha A dagger, exponential minus alpha star A. This is the definition that we have studied for this, and along with there is a Gaussian factor which is equal to alpha square minus beta square. So, this is the expectation and or rather the inner product of the two coherent states. Now, it has to be seen that whether these two coherent states are orthogonal. Now, in order to see that, let us see the end states, that is this one and this one, and they can be expanded in terms of basically the exponential can be expanded, which is exponential minus beta A plus and all that, and then you have an exponential minus alpha A rather alpha star A, which is equal to 1 minus alpha star A and plus all that. Now, it is very clear that all these terms with A dagger and A in both at the edges will yield 0 when they act on vacuum. So, the ones that are saved or rather that are survive, those survive are the ones, and in which case we have we can actually ignore them, and we can write this down as 0. And now, we do the expansion to the other quantities as well, which are this and this. So, this is equal to 1 plus beta star A plus 1 by 2 factorial beta star A square plus all that, and then we have a and then we have a 1 plus alpha A dagger plus 1 by 2 factorial alpha A dagger square, and so on, and then it is 0, and of course, these are there. And of course, we also have the exponential this factor, which will let us write them here, exponential minus half alpha square minus beta square. So, this yields so then this is like 2 1 by 2 factorial root over 2 factorial. So, this you will get it if you see it carefully by multiplying term by term and plus 1 beta star and plus a 0, which are for different values of these basically the Fogg basis, which would generate by successively operating the A dagger and things like that, A or A dagger, and this has to be taken. So, this is really a bracket, not an angular bracket, and then this is multiplied by a 0 plus a alpha 1 plus a 1 by 2 factorial root over 2 factorial alpha square 2 and all that plus all this and so on. So, this and of course, this whole thing is multiplied by the exponential half, just write it neatly. So, this is alpha square minus beta square and so on. So, that is that is what comes out of this inner product of two coherent states, and just to remind you that we are trying to find out that whether two coherent states are orthogonal or they form a complete set of states. And so, this if you use the orthogonality of the Fogg basis, that is this equal to delta n m, then your beta alpha becomes equal to exponential minus half. So, there is a sign problem that I have introduced from the beginning. There is a plus there and there is a plus there, there is a plus there. So, this is alpha mod square plus a beta mod square, and 1 plus alpha beta star plus a 1 by 2 factorial alpha beta star, and so on, plus. So, this is nothing but exponential, that is the expansion of the exponential alpha beta star. So, it is exponential alpha beta star. So, this is equal to exponential minus half alpha mod square plus beta mod square plus alpha beta star. Now, if you look at this alpha minus beta mod square, so that can be written as alpha minus beta and alpha star minus beta star, which is equal to alpha mod square. If you just open up, that is multiply term by term, it is alpha square plus beta square minus alpha beta star plus alpha star beta, and so this is equal to, so beta alpha mod square is nothing but equal to exponential alpha minus beta square. So, the main thing is that after doing all this algebra, it turns out that the coherent states are not orthogonal, and in fact, they are only orthogonal when alpha is much greater than beta or alpha minus beta is much greater than 1. So, in general, coherent states are not orthogonal the transition probabilities only vanish if alpha minus beta much greater than 1. So, this is the conclusion for this, and but of course, they form a complete set of states. So, this I will not prove it here, but one can show that, which we may actually do it in a tutorial, that the coherent states form a complete set of states. So, even if they are not orthonormal to each other, they still form a complete set of states, and which can be shown by showing that this summing over the coherent states, this gives up 1, and so on. So, these are some of the properties of the coherent states. Let us now go to study what are called as squeezed states. Okay. So, this is very well known that the uncertainty principle which Heisenberg had proposed puts an impediment in the study of various quantum systems, or rather precisional measurements of quantum systems, and this of course is sort of dampens the enthusiasm by the quantum engineers, where they want to do a lossless transmission of quantum information by optical means. So, just to summarize that uncertainty principle is an impediment to transmission of information by optical means. There are of course quantum noise. So, quantum noise is an essential ingredient to optical communication. So, the very relevant and pertinent question in this regard is that can we beat the uncertainty principle or can we reduce the effect of the uncertainty principle, and so this is the question that we want to box it, and possibly the squeeze states give a clue to this answer. So, it is important to understand that the uncertainty principle is actually a statement about the area in the phase space. So, is about area in the phase space, which what we mean by that is that it is this product of a small the pixel in the phase space. So, if we can devise a procedure to deform and squeeze this area, which can be effectively used for reducing the noise. Such squeezing process is of course, it does not devalidate the uncertainty principle, but is just an engineering that one can think of doing, and the possible means of doing it is via squeeze states. We will see what that is. So, the question that one asks is that can one squeeze or deform this area in the phase space. Okay. Again, a question that we want to box because it is a very relevant question, and to keep in mind that this procedure does not devalidate the uncertainty principle that we all are familiar with. So, let us see that how it can be squeezed. Before that, let us try to see some basics which we already are quite well aware of, and consider two non-commuting operators. A and B, I mean which are conjugate to each other, such that X and P commutated. Okay. So, so let us do this commutator, and let us write this as I C, where C is another. So, these are Hermitian operators, just like our P and X are. So, C is another Hermitian operator, So, in general it is a Hermitian operator, but it could be just a C number in some cases that we will just see in a moment. So, this is the commutation relation and it does not commute. Okay. The commutation of these two Hermitian operators give me another Hermitian operators, which is I C, and the uncertainty principle satisfies delta A multiplied by delta B, that should be greater than equal to half of C, where C is the as I told, it is a Hermitian operator, and we have taken an expectation value of that operator, and this expectation value is taken with respect to some state psi. And as usual, our definition of delta A is nothing but A square average minus A average square, and similarly for B and C, etc. So, as I told that the expectation value of A, B and C are calculated within some given state psi, and this state psi, the expectation values are computed within a state psi, and this psi will earn a name as a minimum uncertainty state if the one of the observables, say delta A, will satisfy certain relation. We will just write that. So, this psi will be called as, or rather will be called as a better word, will be called as a minimum uncertainty state provided so if delta A and delta B, they follow an equality rather than an inequality which appears here. So, that is the minimum that is the minimum uncertainty, and they would follow this relation where an equality exists. Now, these states will be called as squeezed if one of the observables say A satisfies a delta A square should be less than half C square. Of course, along with that the minimum uncertainty condition has to be satisfied. So, a state can actually satisfy a minimum uncertainty condition, but may not satisfy the squeezed condition as it is written here. But for a squeezed state to occur, this condition has to satisfy has to be satisfied along with what we have just said. So, delta A delta B should be equal to half of C, and this will be called as, so this is called as ideal squeezed states. So, the whole idea is that the quantum fluctuations of a squeezed state in one observable, say A, are reduced below these half C if at the cost of the fluctuations in the other observable. So, let us write this because this is an important statement. Thus, quantum fluctuations of a squeezed state in one of the variables or observables say A are reduced to values lower than half of mod C at the expense of fluctuations. In the other observable. So, let us give some examples in order to validate our claims, or at least to check the definition of the squeeze state. So, you remember that we have introduced the canonical variables or observables x and p in terms of A and A dagger, and we are going to take those say A equal to half of A plus A dagger and B equal to 1 by 2 I A minus A dagger. So, if you simply so these are our x and p, as we have said that these applies to two canonically conjugate variables which could be x and p. So, if I take A and a B commutator and want to see that how it behaves, this commutator has a value which is I over 2. So, it is very clear that C is equal to 1 here, which is a constant. So, the Heisenberg uncertainty principle takes delta A into delta B should be greater than half. Okay. So, that is the uncertainty principle. Now, let us consider the expectation values of A and B and the variances delta A and delta B within the coherent states. Okay. So, define, so coherent state is given by alpha, which is equal to a d alpha and 0. Just to reiterate the notation, 0 is the vacuum, d alpha is the translation operator which produces an state, coherent state alpha that is written with a ket on the left hand side. So, my alpha A alpha that is equal to A alpha plus I B alpha. So, this is equal to 0 d alpha A d alpha. And this is nothing but equal to alpha. So, it is very clear that A alpha is equal to real value of alpha and B alpha is equal to imaginary alpha. So, one of the canonical variables has an expectation with respect to the coherent state, which is real part of alpha, and the other one, the imaginary one, has got an overlap in the coherent state as imaginary beta. So, I mean sorry, imaginary alpha, where alpha is of course a coherent state. So, so now if we want to calculate the variances, so that is equal to alpha delta A square alpha, which is equal to 0 delta A square 0 equal to 1/4 alpha delta B 0 alpha, which is equal to 0 delta B 0, which is equal to 1/4 itself. So, the coherent states are indeed minimum uncertainty states but whether they are squeeze states or not, that we are not sure, but they are definitely minimum uncertainty states. These are so now the squeezed states, as we said earlier, offer possibilities of beating the quantum uncertainty, the quantum uncertainty limit in measurements. So, let me box this. This is an important statement. So, however, neither Fock, which is n, nor coherent, which is alpha, are squeeze states. So, in fact, one can actually calculate that delta A equal to delta B equal to half for coherent states, whereas delta A equal to delta B equal to half 2 n plus 1 for the Fock. So, this is for the Fock states. So, it is clear that the Fock states are actually the states in the occupation number basis, which was quite largely used in dealing with quantum harmonic oscillator. So, a squeezed state can be obtained from a coherent state by applying a squeezing operator which is S as by xi, which is xi star a square by 2 exponential minus xi a dagger square by 2. So, S xi acting on a vacuum which is 0. Now, it is important to understand that the coherent states are actually built from the vacuum states by the translation operator. So, if the translation operator yields 1, then coherent state yields a vacuum and there is a special vacuum state. And so, if S xi is made to act on 0, that gives me a state coherent state xi. So, this acting on 0 gives me xi, and S of xi acting on alpha gives me another state which is alpha xi. So, these are the they show that S xi operating on the trivial coherent state gives a xi which is a coherent state, and S xi acting on a coherent state gives another coherent state which is alpha xi. So, the in fact, the squeeze states are of four types. One is the number squeeze states, two is the phase squeeze state, and of course, in addition to that we have a space squeeze state and a momentum squeeze states. So, let us give some demonstrations or pictorial representations of these states. So, let us look at so this is my A axis which is real alpha, and this is my B axis which is imaginary alpha, and so there is a vacuum state and this vacuum state can be translated to get a coherent state. Pardon this shapes that are not coming very well. So, these are intended to be circular. So, these are squeezed. So, there is a vacuum state and this is a coherent state and coherent state which is all we know that. So, there is a d alpha operation that gives a state. So, a vacuum state becomes a coherent state, and similarly for the squeezing part. So, there is a this and then it is this. So, this is A, this is B again, this is real part of alpha and this is imaginary part of alpha, and so this is of course a squeezed vacuum. So, we have simply written it as xi, and again this is operated upon, and one gets a coherent squeeze state. And this is given as alpha xi according to the definitions that we have given. So, this is more or less the introduction about the coherent states and squeeze states. They are taken up as applications of the quantum mechanics on quantum harmonic oscillators that we have learned. And of course, there are many examples that are used, I mean, in optical communications, in teleportation and so on, and various branches of optomechanics. Will not go into very specific details of these applications, but rather refer to you. References on squeezed states are one is a YB band. So, it is light and matter and electromagnetism, optics, spectroscopy, and lasers, and it is a Wiley publications. The number 2 is Scully and M.S. Zubairi. And so, this is a quantum optics book. We will give you this, let me just type out this, and this is from the Cambridge University Press. Okay. So, these are some of the references on the squeezed and the coherent states, which you may want to look at, and we will move on to another topic.